This is Thejas, like Bipul, and I'm Siddhartha, and we are here to talk to you about the semantic search efforts that that are afoot at Flipkart. Right? Search. You're all familiar with search. You just type in a few words into a box, the words go off somewhere, a search engine finds documents which contain those words and return them to you. Right? Quite simple, everyone is familiar with it. But what is semantic search? Well, the goal of semantic search is the same as search, but do it better than search, do it better than plain old search. The goal is to get more relevant results, results that are more useful for the searcher who is firing that query. And the means to do that is by understanding the intent of the searcher and context in which the query is fired. Right? Let me give you a couple of examples of where regular old search doesn't cut it and we need something more, we need to understand the query better than that. Take the example of a search called red shoes. Right? When someone searches for red shoes, they're probably looking for shoes that are red in color. But if we just go the traditional route of find words, find documents which have those words or find products which mention those words, we get back results like that. There are a couple of products there which are red in color, but just about. The rest of them are from products from the brand Red Tape. Just because they have the word red in their title, which we usually consider to be very important, we have returned them. But if we had understood this query better, we would have done a much better job of that. Let's take another example, right? United Colors of Benetton, right? Looks quite good actually, from the look of it. All results are UCB shoes. But the problem is, UCB doesn't just sell shoes. It sells a lot more. In fact, most of you probably have not even known that UCB sells shoes. Right? We associate it with t-shirts, we associate it with jackets and whatnot. Where are those results? The reason these came up higher is because these are more popular than the t-shirts or the jackets, and they match the text as well as the t-shirts did. Right? So this is what we're trying to solve with the effort of building a semantic search engine. But before we get into how we did it and how we went about doing this, let me walk you through what search means a little more formally, right? What are the various stages a search query has to go through before you get back the results? This will be useful context to understand the rest of the talk. Right? Normally, when we think of search, we think of it as in two phases. Phase one is the matching phase, and phase two is the ranking phase. Right? In the matching phase, we take the query, let's say Samsung Galaxy, and we break it up into individual terms, what is known as a tokenization phase. Right? These words are then matched against an index, what is known as an index of documents, which returns matching documents. That is, it returns products which have those words. Our next job is to take these and to score them. That is, we have to say, for this query, this particular product, how relevant is it? Right? And in order to do that, we use some kind of models. A simple example of a model could be, if there is a match in the title phrase, give it a weight of 20. If there's a match in the brand field, give it a weight of 15, author field 10, and the remaining text 5, and something like that. Right? Once we have the score, we can take the scores and we can sort the results. And boom, we have the search results we need. Right? That's all. That's what a simple search goes through. But the problem here is that each of these phases, and there's more going on in a search engine than what I've described. This is a gross simplification, but should be sufficient for the purpose of this talk. The thing that we want to do is we want to turn each of these phases here, each of these boxes we have shown here, and we want to make them more intelligent. We want to make them understand the query better and use that understanding to do a better job than they do today. Right? So we want to turn the matching phase into a semantic matching phase, where we understand what each term means. The example was the red shoes. We want to understand that red is a color and shoes is some kind of a category. It's a subset of our products, and we want to use that fact. We want our indexes to be smarter. We want our indexes to have information which is deeper than just the words in the document. We want our ranking, our scoring to be smarter. We want it to understand that when somebody types in UCB, they mean t-shirts more than they mean shoes. And then similarly, we want our sorting to be smarter. We want to sort and give results which has a combination of a good spread of results. We don't just want shoes, we want t-shirts, we want shoes, we want jackets, we want the whole plethora of things that match the query, right? And let's look at what a semantics engine really holds in that sense, right? What are the things that a semantics engine needs to do? Number one, it needs to understand the intent of the query. Remember, I was just talking about understanding the intent. A couple of simple examples would be, if the user typed Jeffrey Archer, we want to understand that the user is looking for books by the author Jeffrey Archer. We don't just want any products which have Jeffrey and Archer as part of their name, right? We want books by the author Jeffrey Archer. Or if the user types S3, we want to understand that they are looking for one particular phone, one of the two colors of this particular phone called Samsung Galaxy S3. Another thing we would want to understand is the context in which the query has been fired. So going back to another example, Samsung, let's say user type Samsung, what is the likelihood that the user is looking, Samsung sells a lot of things, right? Samsung sells mobile, Samsung sells refrigerators, Samsung sells laptops, tablets. What is the user probably looking for? On Flipkart, for example, it turns out to be mobiles most of the time. We want to understand that, and we want to understand it in the context of Flipkart, not just in generally, right? Or when somebody types children books, we want to understand that books about Geronimo Stilton are more important. They are relevant to books. It's not about finding books which say, hey, I'm a children book, right? We don't just want to return books which have a children's book in their title. We want to return any books which are children's books. That's understanding the context of the query. And lastly, we want to understand similarity, conceptual similarity between terms. A simple example is, let's say somebody types Nike bags. And just suppose that we don't sell Nike bags, but we sell Adidas bags, we sell Reebok bags. They'll probably fit in the need as well as Nike bags, at least in the absence of Nike bags. And we would want to understand. We want to understand that Nike is a similar concept to Adidas or Reebok, right? Or if somebody types maroon shirts, and let's say we don't have many maroon shirts, but we want to be able to understand maroon as a color, we want to probably get its RGB value, find other colors, shirts of other colors, which are close enough to that color, right? Maybe our catalog describes them as red shirts. Maybe it uses some other fancy name for the color that we do not understand, designers do, but let's say that's what it is, right? We want to understand all these things really well so we can do a better job of serving the results.
All right. So how do we go about understanding the query? So one obvious and very straightforward way is to look at what users did in the past when they fired that particular query. So that takes us to Clickstream analysis. So a user comes to Flipkart, fires the query shoes. Then what does he do next? He can go click on one of these categories, he can go click on one of these filters, or he goes and clicks on one of these products. And a click on this actually signifies that for the query shoes, he is actually interested in these refiners to get better results. Now, if I were to leverage this data to promote these results higher up in the next searches, then I've solved the problem. I've made it easy for the user to find the products he's looking for. So what all can I extract from Clickstream? So user came in, fired a query. I can see which product attribute exactly did the query terms match. So what do I mean by that? So user fires in a query like Mahatma Gandhi, and I can go check, okay, 64% of the people went and clicked on products where author is Mahatma Gandhi, and 36% of the people went and clicked on books where title is Mahatma Gandhi. This is a direct feedback from the user saying that this is what I'm looking for. And these are, in some sense, probability distribution saying that 64% of the people are more probably looking for books by Mahatma Gandhi than books related to Mahatma Gandhi. Another example, the one which we took up in the demo, red shoes. So we see that 74% of the people prefer red colored shoes as opposed to 10% of people who prefer red tape shoes. Now, this actually solves our first problem, trying to find out the direct intent of the query. Now, we would want to go to the, how do we get the context of the query given this Clickstream data? All right. Well, we can see what all navigational units, what all filters and categories that the user go and click on. So after a query dual SIM, he goes and clicks on Samsung 40% of the times. he goes and clicks on HTC 20% of times, and so on and so forth. So these distributions give a direct correlation between the query, dual sim, and how related is it to the particular filter. And these can again be leveraged when the query gets fired again in the future. So navigational intent is great. It is direct feedback from the user saying that, okay, dual sim, and I went and clicked on Samsung to find better products. Now, this can pull out great patterns when the thing we are filtering based on is a part of the website. So it can pull out stuff like for Samsung mobiles is really important. But it can't do children's books, and Geronimo Stilton is really important for children's books because Geronimo Stilton is not a part of the website view page. So how can we figure that out? Well, we have all the products that the user went on clicked on, and these products have all the attributes that are necessary. So let's say I have this query, and these are the set of products that got clicked for that particular query. Now, and there is a corresponding weight to each product click. So for current, now we can just assume that this weight is the number of times that particular product got clicked for a particular query. So one way of using this data is I can use this. So whenever this query gets fired in the future, I can remember that this is the products ordering what it should look like, and I can put it on the view. But that will become really like memorizing. We are memorizing what all products to show for a particular query, and it does not generalize very well. So, but these products also have all the attributes associated. These products are made up of attributes. An example product attribute vector might look like this. So model ID is Xperia M, color is white, OS Android, so on and so forth. All the attributes that make up the product. So I can do a simple join between these two and get the attribute weight. How important is each attribute vector? Now from this I can extract, okay, of the products that got clicked, 60% are brand Samsung and 30% is Micromax, but I can also derive information about things that are not filters on the website. So like model ID Xperia M gets clicked 20% of the times, and form factor bar gets clicked 85% of the times, and so on and so forth. But this is extremely large amount of data. To use this at runtime, it becomes really expensive. So I need to extract really good features out of these so that at query time, I can use them for querying and giving better results to the users. So which attributes do I choose? How do I choose a small subset of attributes from all the attributes that I have? Now, the limitation is I can only choose a small set of attributes from the pool of attributes that I have. Now, each attribute has a coverage. Now, something like model ID S3 is going to cover only a small set of products, as opposed to category mobiles, which is going to cover a large set of products. Now, when a user fires a query mobiles, I would want to choose attributes such that it covers the entire domain of products that it represents. But I would want it to choose attributes like OS, Android, color, black, features, HD recording, which are important and which I can promote higher. So when the query is a little bit narrower, say Samsung Galaxy, I would want to pull out more granular attributes like model ID trends, model ID S-Duos, model ID, model ID core to, model ID, some other model ID. So so this is what I have currently, which is given a product, an attribute vector, and how much weight is to be given to that particular attribute vector. This is what I want. For each attribute, how much weight is to be given. For now, let's assume we have a black box model which gives us this attribute weights, given an attribute vector and the product weights. Now, how do I know that this set of attributes that I have chosen is representative of the products that were clicked and the corresponding weights? Well, one way is, say product 1 is made up of attribute 1, attribute 2, and attribute 5, and product 2 is made up of attribute 2, 4, and 6. I can plug back these weights back into the products and compute the computed product weight, identify the computed product weight. Now I have the original product weight and I have a computed product weight. I can find out the error between these two and use it in my learning algorithm to find out what the black box should look like. Now the algorithm itself, as I was saying, for a broad query, I would want to identify broad intents and broad attributes, and for a narrow query, I would want to identify narrow attributes. So we compute the goodness of each attribute. What is the goodness is computed using what is the average weight of the attribute in which this average weight of the attributes in which this attribute exists in some products. What is the, okay. And coverage of an attribute is how many products this attribute cover. Now, finding, the learning algorithm finds out this model using what minimizes the function which takes goodness and coverage and tries to minimize the error. Now, for the error itself, we use root mean square error, and the learning algorithm itself, we use gradient descent. Now, that solves for identifying the context in which the query was fired. Now, Clickstream analysis comes with its own set of biases. So, position bias. So, what is position bias? The products that get clicked for a query is a function of what products we show to the user. So, a product in the first position gets clicked a lot more number of times than a product that gets shown in the 100th position. So, how do we eliminate this bias? So, we can eliminate this bias by weighting the click as a function of the position in which it got clicked. So, a click in the first position will get a much lesser weight as compared to a click in the 100th position. And how much weight itself is to be given is figured out based on the probability that the user goes to the 100th page or 100th position basically, which would be 4th or 5th page. Now, recent data is more important than data that is accumulated over the past. So, for example, 2 states as a query, 2 months back would have meant books, now it means movies. So, this movie, the data for movies, for it to overcome all the aggregated data of books, we will have to weight recent data a lot more higher. So, we use an exponential decay with a very slow decay rate, and the click itself is, the weight for a click itself is a function based on the time in which the click was made. Now, Clickstream analysis has a couple of limitations. So, Clickstream is a great signal, but Clickstream is heavily dependent upon the number of times the query was fired and the actions that were taken for that particular query. So, here is a graph of the queries that get, the number of times a particular query gets fired on Flipkart. So, on the x-axis, you have the queries themselves. On the y-axis, you have the number of times the query gets fired. Oh wait, it's not the number of times, it's the log of the number of times that got queried. So, even after taking a log, we still see an exponential curve in the number of times the query gets fired. So, we have a huge head and a very long tail. This long tail we don't have any data for, and Clickstream will not serve us any good here. So, also Clickstream will not have any data about recently added products in Flipkart. So, MotoG gets launched today, we don't have any data about MotoG. How do we surface up these results? So, we'd go to the next approach.
So, Clickstream model can provide me very good insight into popular queries like jeans. It can give me distributions around attributes like brands. It can give me distributions around the fit that people are more clicking on. It can even give me distribution around the category that people are clicking on. What kind of people are more interested in jeans, men's or women? But when you fire a query such as red shoes for women, for which the Clickstream, the query hasn't been fired enough in the past before, it cannot provide me any good insight into the data. So, how do we solve this? The term red shoes for women is present in our catalog, the product catalog we have. So, what we started by doing is we created an index of these attributes, and when querying this index for the term like red, it gives me documents such as color red, brand red tape, brand red chief. But how do I know which one is important among them? How do I rank them? How do I order them accordingly? Now, let's see what all signals we can derive from out of it. So, the color versus brand, the ranking, how do we do it? Is we can look at the textual match score. As in the term red, I can see that there is a 100% match to the color red attribute, whereas there is only 50% match in the brand red tape attribute. There is also the popularity of the entity. Each attribute occurs in some set of products. the popularity of the entity can be defined as the aggregate of the popularity of the products that it occurs in. Also the recency, as said, two states could occur in movies as well as in books. How do I bump up, how do I surface up two movies as an entity despite of it being old and very low popularity score? As in it occurs in only one product, so how do I bump up, surface up those products? Let's see. So what all information we are missing when we are creating an index out of these product attributes? We forgot to create a relation, we also forgot about, so what do we do when a query like Android mobiles happens, we fire a query to a query like Android mobiles. The term Android can occur in the OS Android KitKat and the title Android programming, the pushing the limits, which is probably a book. When I fire the term mobiles, it can occur in category mobiles and can also occur in title mobile communications. Now, how do I find which combination makes sense out of it? OS Android with title mobile communication or title Android programming with mobile communication. So this information we lost somewhere during around indexing of these attributes. So what we did is we created a relationship, an edge between the entities that we found out during the indexing time. We connect the entities if we find products between them. So when the structure will overall now look like a graph. This graph, how do we building this graph will, for a product like red tape men's shoes, it's going to give me something like this. The entity category shoes, the brand red tape, and the ideal for men. We connect these since we have products for these. Let's see another product, which is Levi's men's jeans. The structure would look something like this. Another query we get is red Nokia mobile. The graph finally will look something like this. Let's take another example. Red tape men's shoes. How will this look like? We have connected all the entities. We know the popularity of these entities by the popularity of the products that they occur in. Now, if I query, then how do I query? Let's take an example. I search for the query like red shoes for men, as previously. My goal is to find out fully subconnected subgraphs in this which contain all of these query terms. So red shoes for men is going to give me these two subgraphs, the one with the color red and the one with the brand red tape. Now how do I decide which one to choose out of it? How do I rank them? I have these signals, the textual match score, the popularity, the edge weight. The edge weight is the aggregation about the number of products it occurs in plus the node popularity itself. So now we can easily rank up the subgraph with the entity color red is more important than the one with the entity red tape brand. Now this as a structure will will result in a direct intent, will help me understand the direct intent behind the query for any sort of query. Now, but we can also use this graph to understand the context behind the query. Understanding the context behind the query is, I am going to explain this by an example, is let's say someone searches for a term query like bags for women. How do I find out bags for women as a term, as a query, does not give me any information around what kind of brands or what kind of color related products the user is looking for. So bags for women will give, when searched in this graph, will give me two nodes, the category bags and the ideal for women as a node. Now, if I want to find out the popular brands among this, I want to surface out brands that has more affinity to women rather than brands that are unigender specific, like brands like Fast Track. So what we do is we find out the brands that are connected to both of these nodes. So which is going to give me something like this: the brand Butterflies, the brand Pepperone, the brand Fast Track, and the Puma. This is order based on the edge weight and the ranking of the score of the node itself. So we are here able to find out that the brand Butterfly is Bumping up products that have brand butterflies or brand pepperone makes more sense than brand fast track or brand Puma. Now this helps us in finding the context of the query. You pivot this around any type of attributes. Understanding conceptual similarity. Now the problem here is mapping unknown terms to the known terms in the index. And also mapping the terms such as Nike bags to Adidas bags, because Nike bags as a query, we do not have products for it, but we have similar products of different brands. I want to surface up those. I want to also surface up when someone searches for specific colors like maroon shirts, I want to show results for red shirts, because despite on the fact that the user is searching for maroon shirts, if we don't have products for it, we might want to even show maroon red shirts or dark pink shirts or similar products. How do we do this? This is our approach number 3, finding out conceptually similar terms for a given query. Now, as said, a user searches for a term like hiking shoes. Hiking shoes, we don't have the term in our index. How do we map it to a term like trekking shoes? Trekking shoes, we have products for them. We have products for brands like Woodland. We have products like Quencha shoes, which can be used as a hiking shoes. How do we find out, how do we map these terms? So what we did is we use WordNet to, so querying the graph for the term hiking shoes is going to return me nodes like category shoes. Now I just have to identify that the terms, what does the term hiking I can map to? So so we picked out all the nodes that are connected to the category hiking shoes, and we used WhoopArmor with WordNet to find out terms that are closest to the term hiking, which will result me in giving me terms like trekking. And I can use this and surface out results like Woodland shoes, Quencha shoes, and so on. Other problem is terms like Nike bags. Someone comes and searches for brand-specific lifestyle products or brand-specific any products. We don't have products for it, but we have other products. Someone searches for a mobile brand that is off late launched. We don't have products for it, but we have other mobiles. We want to show them those products. So Nike bags is what we do is we know the term Nike is a brand, and the term bags is a category for me, because we have products in other categories for the brand Nike. So I use Nike and I use the co-occurrence similarity of this brand and find out what all other brands that the people have applied this filter with. So this will returning me brands like Adidas or Puma. And we show up results for Adidas bags and Puma bags as well. Then there is color similarity. Color similarity means we have queries, user search for maroon shirts, and we map this maroon to their RGB space. And this RGB space, we find out other similar closest RGB values that we have products for. We can map maroon to red and dark pink shirts, and we can show results for them. And this is how we show. This is one of the examples. Like the user search for high ankle Converse sneakers. We don't have Converse sneakers for high ankle. So we find out a conceptually similar brand, that is Puma, and show the results for them. And this is how we understand the conceptual similarity using graph.
So now we have all these 3 different components that we have modeled for semantic engine. Where does it all fit in the big flow of search? So Sherlock is the service that provides search in Flipkart. So website and all the apps make requests to Sherlock by giving it the query, and Sherlock responds with all the products in whatever semantically ordered fashion. All the user activity on the website then gets logged, and these logs are then analyzed in the backend Hadoop MR world. And this data is fed back into the Clickstream model. The query itself first goes through concept analysis, then goes through the catalog graph and Clickstream, and the output of these 2 is given to the ranking and the classification engine, which we'll be looking at in the next 2 slides. Okay, in ranking, the signals from the graph and the clickstream analysis is combined, and an equivalent index query is created and fired on the index. So we've also made, we have also added an hook on our index to ensure that if in clickstream it says that 80% of the people prefer mobiles for a particular query and 20% of the people prefer accessories, we bring about a similar distribution in the result set that we have identified. Say we take 50 products out of one of these result pages, you would find a similar distribution of 80% is to 20% results in that result set as well. Also, so the intents identified is at a very granular level. So when someone says S3, the semantic engine is going to tell you that this is actually model ID S3. This is way too granular data. So classification is just generalizing this data to higher level terms, like identifying what is the category of the query. Say, is it a lifestyle query? So when someone says red shoes, we automatically identify that it's a lifestyle query. When someone says Samsung, we automatically identify it's an electronic query. When someone says S3, we automatically identify it's a product query. So where can this data be used? This will help us make higher decisions at a much higher level and provide a different experience based on these classifications. So when someone searches for pen drive, we have identified that it's a category query. That is, it is a category, and we can redirect him to that specific page wherein he can be eliminated of all the other products, which are essentially noise in this case. So the tech stack that we used, so our index is Solr. The Hadoop jobs run on MapReduce and Cascalog, the basic Java MapReduce. And for the graph, we use Neo4j graph database. Semantic search is currently in A/B testing now and will be live in some time. So this is what red shoes you would have seen when you have searched for earlier. This is what you see now, where you see red colored shoes. Earlier, you would see only shoes for United Colors of Benetton. Now you would see shirts and slippers and all the categories, all the diverse categories that are available. And that's it. Thank you.
In the search portion, the tokens which you are considering are only unigrams, right? I mean, individual words. Instead of going for unigrams, why not go for bigrams or trigrams? I mean, won't they reduce the number of false positives which you are getting while searching?
So usually what we end up doing is we consider the individual terms as well as bigrams, trigrams, whatever, right? If the bigrams match, then they are given higher preference. But if the bigrams do not match anything by themselves, then we go down to individual. So you have to realize that the document set that we are working with here is very structured document. So we have things like brand, red tape. And the text shoes itself is in a separate attribute. So it's not like contiguous text, which is what most of text search deals with, right? Bigrams do not end up yielding as big a return, except when they are referring to specific categories, specific brand names, and so on. Okay.
Are you planning to combine user content data also in the semantic?
Yes, that would be our next process. So you saw the context is currently heavily related to the query itself. For a query like Samsung, we would say that mobiles is important. But when the user pivot comes in, probably for that particular user, cameras is more important. That's something that we are working on.
So there was a talk about know your customer, right? Just earlier, just an hour ago. They're trying to generate insights. They're trying to figure out look at user activity from the past and understand a user. What search would be doing it is in turn consuming that data and deriving context both from the query and that data. Put them together and we have a much richer source than just the user context either or just the query.
Regarding brands, let's say Nike, Puma, Adidas, like you are kind of equivalencing them. So is it auto learning or you are like?
So it's basically found out based on the fact, how many times is the filter getting applied together? Most people apply similar brand filters.
Yes, it's simple co-occurrence analysis based on the co-occurrence of the filters or based on the clicks on products. So let's say, for example, people have searched for bags right? And we see that a lot of people, or let's say they have searched for shoes, and we see that a lot of people apply Nike, Adidas, Reebok filters together. Or they click on results. When they click on results, they click on Nike results as well as Adidas results. So for that query, these filters have co-occurred and these products have co-occurred. And from that, we derive that, okay, these have a similarity.
In the context graph scenario, in the context graph scenario, so basically you're clustering to different categories, right? So now when the distinction between the categories are actually diminishing nowadays, so watch can be an accessory, used to be an accessory, now it can be also come under the electronics, right? Samsung gear and stuff like that. So basically with all your clusters, if each of them map to your electronics category, you will end up with a huge big cluster. Right? How do you solve the problem?
So here's the thing, right? We actually oversimplified when presenting here. Almost everything we get, when we said, for example, that Samsung means the category mobiles, it's not really that that's not what we get. We say Samsung means mobiles with a probability of 0.7, and it means tablets with a probability of 0.2, and so on, right? It's at that level, right? When we talk about at a category level, it goes at that level. And our categories are not defined at a very, very high level. They're not electronics, right? We try to take them to as low as possible. So mobiles is a category that we talk about. Mobile cases and covers, right? Just the covers is a category that we talk about. Right? We're not trying to generalize it to a point where most of the value gets lost. Electronics is an example. We actually tried an approach like that early on and realized the same problems and then went back to this one.
Thanks.
For the graph structure, like, are you using tools like RDF, OWL, Turtle, and is to the semantic web way of representing things?
No. So the graph is quite, it's not really quite like that graph, if I may say so. It's just a way for us to query and find. So the most graph theoretic algorithm that we use is finding fully connected subgraphs. Right? It's something that simple graph databases like Neo4j are able to give us very quickly. The graph itself is created out of a catalog, not of queries or anything. So its size is limited to the size and the concepts within our catalog.
You said that you would be including user context while displaying the results after this, right? So let's say I was a user. I have previously bought a Samsung camera from the site. Now next time I'm searching for Samsung, if you're displaying camera for me, would that be relevant? I've already bought a camera.
So ideally what we would want to understand is, ideally, and we have no way of doing that right away, but we're working towards that. We understand that you have bought a Samsung camera in the past. We probably suggest Samsung accessories for that very camera, right? We suggest complementary things for that camera. But if we think that that camera is too old now, maybe you bought it 2 years ago, 3 years ago, maybe you're looking for replacement, maybe we will suggest an upgrade to that camera. Now we understand what kind of cameras you have. We understand that you need DSLRs. Maybe you like Samsung DSLRs. We'll suggest more Samsung DSLRs. Samsung doesn't sell DSLRs, but that's a different problem.
There are some 3,000 entities and some 3 million entities and some into some 12 million entity relationships that we have got.
So how do you do the subgraph in that real time?
So for each terms, we said we connected these nodes. So we pick up two terms each time, and we try to generalize, get the connected graphs itself. So the next set, we trying to find out the neighbors that is already connected to the first set of results.
So essentially we have an index over the graph and its edges, and then we query on those indices to get the nodes itself.
Okay. And may I also know how many search events are typically seen at your site? Events as in
Number of
percentage wise.
I think it's about 6 million searches a day.
6 million.
And of those, the thing of interest is that of those, about 4 million searches are queries, we have never seen in the past.
Right.
They're brand new each day. So that's what Thejas was talking about, the really long tail, right? Of 6 million searches we see, 4 million we have never seen ever in the past. Yeah.
Thanks.
Do you plan to do free text search also? Can you search Android phones which do not have mobile dual SIM support or stuff like this?
So if you try, actually, which do not have, you're referring to the idea of natural language processing, understanding the query, breaking it down, and understanding it the way we would understand an English sentence. We have not ventured into that direction yet.
This would be one pre-step to that. I mean, we have identified that Android is the OS, and the next step would be not to show Android when you search for it. This is one level before that.
Although we're not yet sure that's going to be of value, it may as yet be of value, because as of now we don't see a lot of queries of that sort. We don't see users searching in that way, probably because they have been coached through years of searching in most other search engines like Google, which do not really understand queries in that way, right? People who are coming to search have all been coached by Google, right? They think the way Google makes them think. Right? We have to work in that context largely. All right. Nice. All right. Thank you.